We're going to take a look at a proof for the Triangle Sum Theorem. So the Triangle Sum Theorem, I would make the argument, is probably the most interesting theorem that we've looked at so far because it actually proves something that is interesting, and it's something that is non-trivial, something that we've seen before but just maybe not have known why. And so what it says is that if a polygon is a triangle, then the sum of the interior angle measures is 180 degrees. Okay, so I think we've all known this probably for a while, that whenever I look at the interior angles of a triangle, that their measures will always add up to 180 degrees. And so the question is why is that the case? And also a better question is why 180? And so we'll address that here in a second. So I'm going to start off with a diagram to look at. Here's my diagram. It's just a triangle. There's nothing interesting about it. I don't want this to be necessarily a right triangle or an acute triangle or an obtuse triangle. It's just a triangle. It has no special properties. And the thing is that there's not a ton of information to go off of. I'm going to label my points, of course. But I don't really have anything to work with. So whenever I have a problem that I don't know where to start, what I can probably do is if I can make some changes to it so that it looks like a problem that I've seen in the past, then I'll be on my way to actually solving it. So what I'm going to do is, when I think about 180 degrees, what I think of is, a line, a straight angle. So a straight angle, its measure is 180 degrees. And so I want to talk about that. And what we've been talking about a lot recently is parallel lines. And so if we can somehow combine, the idea that lines or straight angles, their measures are 180 degrees with parallel lines, and then we'd be probably pretty well off. So I'm going to focus on this bottom side of the triangle, and I'm going to construct a line that is parallel to it. So something like this. Okay, so I'm constructing a new line here. I'm going to call this line P and line Q, and I'm constructing them such that they're parallel to each other. And so now I have something to work with here, because now I can start talking about angles that are congruent and be well on my way. So I'm going to put some labels down here. So I'm going to call this angle 1, angle 2, angle 3, angle 4, and angle 5. And then I'm also going to add some points that I can reference. I'm going to call this point D and this point E, and we'll see why that is in a second. Okay, so now I have some angles to talk about that are being congruent, because now I can actually relate 1 with 3 and 2 with 3 somehow, but we'll get there in a second. I'm looking back and I realized that I couldn't spell. This is polygon. There's a G in there. Oh well. Okay, so let me write my proof or my given. So my given, one thing that I might want to start with is just talking about the fact that ABC is a triangle. But that's we're just going to take that from the diagram here, because that's really what my hypothesis is. But then what I did was I drew in these parallel lines, so that's an additional fact. So P is parallel to Q. That's really my given here. And then what I'm trying to prove is the fact that the measure of angle 1 plus the measure of angle 2 plus the measure of angle 3 adds up to be 180 degrees. That is my goal. Okay. So let's go ahead and start with that information. We'll see where we can go from there. So statement 1 is just my given. That's P is parallel to Q. That's statement 1 over here. That's given. Okay. All right. So where can I go with this? So I know that angles 4, 3, and 5 add up to be 180 degrees. And so if I can end up writing an equation about that, and then since I know that 1 and 4 are congruent and 2 and 5 are congruent, I can probably make some substitutions. So I need to do one of those two things first, either link these angles together or talk about these three as a set. Let's talk about the set. Let's talk about the fact that 4, 3, and 5 all add up to make this larger angle here, DBE. And so I'm actually going to start there, talking about angle DBE, and I'm going to say that angle DBE is a straight angle. So this is something that we haven't really done before in a proof, but it's something that we can assume to be true from the diagram. I can tell when lines are straight. I mean, all lines are straight, but specifically, I guess, angles, when they are straight, I can tell that on a diagram. If an angle is a line, then it's got to be a straight angle. So this is actually one of the other things I can assume from a diagram. So assumed from diagram. Okay. So then what I can talk about is that, well, what do I know about straight angles? What I know about straight angles is that their measure of angle DBE, is 180 degrees. So now I've got 180 degrees into my proof here, which is great because it's going to be somehow linked back with what I have at the end. But how do I know that? Well, it's a definition of what a straight angle is. So an angle is straight if and only if its measure is 180 degrees. That came from the fact that it's a straight angle, the previous statement number 2. And now I'm going to have to talk about somehow link 4, 3, and 5 with angle DBE. And so I'm going to use a postulate that we've known for a long time, but it's going to seem kind of weird because I haven't used it in this way before. But I'm going to say that the measure of angle 3 plus the measure of angle 4 plus the measure of angle 5 is equal to the measure of angle DBE. And the reason for that is, and I'm cheating a little bit here if I'm being honest, it's the angle addition postulate. So the angle addition postulate actually really just tells me about whenever I have two angles that add up to make a larger angle. And so, I'm cheating a little bit and taking 3 instead. What I really should be doing is talking about the measure of angle DBC being, angle 4 and angle 3 added together. And then what the measure of angle DBE is the measure of angle DBC plus the measure of angle 5. That's a whole mess, though. I don't want to do that. So we're just going to say the angle addition postulate to say that 3, 4, and 5 add up to be the measure of angle DBE and call it a day. Okay, so now I have some linking going on here. I have the measures of angle 3, 4, and 5. They're equal to the measure of angle DBE. Measure of angle DBE is equal to 180. I could substitute that right now, but I'm actually save it for later and do all my substituting at one point. But I can see how I'm starting to link these together. Now I actually need to link 1 and 2 with 4 and 5. And so I'm going to do that next. I know that angle 1 is congruent to angle 4. And the reason for that is, well, these lines are parallel, and 1 and 4 are alternate angles. And so I can say that if the lines are parallel, then the alternate interior angles are congruent. The alternate interior angles are congruent. Great. And where does that come from? Where did I say the lines are parallel? That was back in 1. And I can do the exact same thing for 2 and 5. So this is statement 6 then. Angle 2 is congruent to angle 5. Statement 6. If the lines are parallel, then the alternate interior angles are congruent. Alright, and that is also linked back to 1. So, now that I have these are congruent, what I'd really like to do is substitute these back in, but of course I can't do that because these are congruent statements, so I need equality statements. So I need to do the tedious step here, well, 2 steps, of saying that, so step number 7, the measure of angle 1 is equal to the measure of angle 4. And this is just my definition of congruence. 2 angles are congruent if and only if their measures are equal. And that comes from 5. And I'll do the exact same thing for step number 8, just for angles 2 and 5. The measure of angle 2 is equal to the measure of angle 5. I feel like the more videos I've made, the worse my handwriting has gotten. Angles are congruent. That's okay. I can read it. I don't know if you guys can, but oh well. If their measures are equal. And that comes from 6. Okay. Now here is the mega substitution step here. So what I've got is that I can substitute, let's see, 4 and 5 in for 1 and 2, or sorry, the other way around. 1 and 2 in for 4 and 5 in this equation. And I can substitute 180 in for the measure of angle DBE in this equation. And so I can do this all at once and say that the measure of angle 1 plus the measure of angle 2 plus the measure of angle 3 all adds up to be 180 degrees. And I'm just going to cite the substitution property. And I'm going to, let's see, I have to talk about statement 3, 4, 7, and 8. Okay, so let's talk about the interesting part of this. So we've finally proven something that is, an interesting finding, that the sum of the interior angles is 180 degrees. And so the question is why? And the answer is really, well, it has everything to do with the measure of what we've decided a straight angle to be. If at some point in time we had decided the measure of a straight angle was instead a different degree measure, well, then the sum of the interior angles of a triangle would be that other degree measure then. And so there's nothing special about 180 other than the fact that it's a measure of a line, right? And so another way of saying this is that, well, for a polygon, if it's a triangle, the sum of the interior angle measures will be equal to whatever the measure is of a straight angle. And that's the interesting thing, that it works out that way. And so really, the 180 isn't special. 180 is only special because we've decided that it is. But nonetheless, is an interesting finding here, and that's the fact that no matter what triangle we have, no matter if it's acute, obtuse, equilateral, whatever, the sum of the interior angles will always be 180 degrees, and so we'll actually be able to use this a lot in our calculations moving forward.